Hi everybody, welcome back to the channel. In the next few sections we're going to take a look at a lot of examples or a lot of ideas about how a graph of a function relates to the graph of its derivative. That's coming up in the next few sections, but before we talk about that, we actually need to talk about a couple of big results. They have the word theorem attached to them, which means they're bigger, important results that have been proven to be true in math. And so in this video we're going to take a look at a couple of theorems that are fairly big, and then a couple of smaller results that go along with it as well. And these kind of talk about how when you know some features about a function f, what happens with its derivative. So let's just go ahead and kind of jump right in. One thing we're going to focus on with these examples or with these theorems is looking at the criteria that's needed in order for these theorems to be true. So in the first theorem there's actually 3 criteria. In the second theorem there's only going to be 2 criteria. We're actually going to have some problems that say something like verify the criteria, and so I don't want you to just kind of gloss over those or forget those. I want you to make sure that you understand what are the criteria that need to happen in order for this result to be true. So we're going to kind of check those and make sure that those things happen. Now they're going to be very similar. In fact, we almost shouldn't think about this as 2 different results. We almost should think about it as almost exactly the same result with just one criteria different. And because the one criteria is different, it kind of changes the result a little bit, but they're very, very similar in nature. Okay, let's go ahead and take a look at the first one. The first one is something called Rolle's theorem, and it has 3 criteria here. In fact, we've seen kind of the first 2 criteria a little bit with some other results. So the first criteria says that f has to be continuous on a closed interval, and the second criteria, f has to be differentiable on an open interval. And by the way, these 2 criteria are going to be really important criteria for us moving forward, and these are going to show up in a lot of different results. So I'm not going to say that in every problem we always assume f is continuous and f is differentiable, but that is going to happen a lot. So may as well just kind of get used to those 2 criteria for now. And then this Rolle's theorem has a third criteria that's a little bit unique. This is a little bit different. That says that f of a is equal to f of b. I want you to kind of think about on a graph, what does that mean for a second. Let me go ahead and draw a graph on here. And we're going to start at a and we're going to end at b. And to say f of a is equal to f of b means that at both of the endpoints, they both have points that are at the same height, same output. Now the function could do a lot of things in between there. Okay, so you might have your function, this is a very boring example of this case, but the boring situation is, what about if you just have a function that's kind of a straight horizontal line all the way across from a to b? That's not a very interesting example, but it is one we could consider. And so notice the result of this says, the result of the Rolle's theorem says that if these 3 criteria are met, then at the end there is a number c somewhere in between a and b. Notice on the open interval from a to b, not the closed interval. So it's not, so c is not one of the endpoints, but c is somewhere in between a and b, where f prime of c is equal to 0. I say that this example is not a very interesting example where you have a straight horizontal line, because if you look at every single point in between a and b, every single point has a derivative that's equal to 0 there, because this is just a straight horizontal line. So not a very interesting example. In fact, what would be a little bit better for us to take a look at, ones that are a little bit more interesting, is what if this graph f kind of goes up and down a little bit. So we could either have a situation where f is kind of strictly up above a and b. We could have a situation where maybe it's down below a and b, or we could have a situation where maybe it kind of goes back and forth. But the idea is it's got to start where a and b on the endpoints have exactly the same output value. And so notice kind of all 3 of these other cases here, and this could do crazy stuff. It could go back and forth all over the place. Now what it can't do is have any breaks or gaps or jumps, because remember, it's supposed to be continuous on the whole interval. Okay, but if you look at all of these, I probably should have drawn these in different colors, but all 3 of these examples of functions that are here have a number c somewhere. We don't know where c is, but there's got to be at least one point somewhere c, such that f prime of c is equal to 0. This notation right here, f prime of c is equal to 0, what we saw in the last video, or in the last section, is that there's another way to talk about this. When f prime of c is equal to 0, we called that a critical value. Or another way to call it was a critical number. So we have a critical number when that happens. And so remember, the criteria for a critical number was that f prime of c is either equal to 0 or f prime of c does not exist. In this case, we're just focusing on the part where f prime of c is equal to 0. Okay, so for example, let's say we have this, the top one that goes up and then kind of comes back down. There's a point up here somewhere where there's a value of c right there, where f prime of c is equal to 0 because it has a horizontal tangent line. And another way to think about this idea of f prime of c is equal to 0 is that for us, in this case, this is not always true with every function, just in general, is that when f prime of c equals 0, you have a minimum or a maximum. Not necessarily always true, but in this example, because f of a and f of b are exactly the same value, this is talking about you are either going to have a local min or max somewhere on your graph. Okay, and remember that when it says there is a number c, it could mean that there is more than one. So that's another way to kind of think about that wording, is it could say then there is at least one number c, such that that happens. So the other graph that kind of goes up and then comes back down, there's actually more than one place where you have a horizontal tangent line. There's kind of one at the bottom, and then there's one at the top up here as well. And so it has to have at least one value of c where f prime of c is equal to 0. Okay, so this is Rolle's theorem. But again, this third criteria of f of a being equal to f of b, that's a really unique criteria. That's kind of strange. If you think about kind of pick a specific value of a, pick a specific value of b, and pick a random function f, there's a really good chance that just with the random a and b and f function that you chose, that it's probably not going to be the case that f of a is equal to f of b. That just does not happen a lot. That's kind of unique criteria. Okay, but that is one of the three criteria that are needed in order to use Rolle's theorem. Okay, let's go ahead and look at the second result, which is really similar to Rolle's theorem, but this one is even going to end up being more important for us because, like we said, that criteria of f of a equal to f of b is kind of unique and rare. Notice what's missing in this theorem here, the mean value theorem, which, by the way, the mean value theorem is the name of the section in our book. And so this is a pretty important result. This is going to show up a lot in different ways, as well as proving some other results down the road. Okay, so there again, we want to think about what are the criteria for the mean value theorem. And so this one doesn't have three criteria, it only has two, and that's because that third one that's kind of unique is just removed. We don't need that one anymore in the mean value theorem. That was only for Rolle's theorem. So the two criteria we need for the mean value theorem are that f needs to be continuous on the closed interval and f needs to be differentiable on the open interval, just like we had back in Rolle's theorem. So I mentioned that you shouldn't think about these as two different results, even though they are. You should kind of think about them as being really similar. It's just one of them has that third criteria and the other one doesn't. Okay, and you'll notice the statement at the end isn't quite complete yet. It says, if these two criteria are met, then there is a number c in the open interval from a to b such that, and so let's go ahead and finish this, and we'll see an example on a graph of kind of what are we doing here, such that f prime of c is not, it's not necessarily going to be equal to 0, by the way, because remember, equal to 0 was just because we had that third criteria where a and b have to give you the same output value. So here's an example of a function where we go from a to b, where there might not even be a maximum or minimum. Maybe f of a is way up here and f of b is way down here, and your graph might do something like this, where you don't even have a point on here where you have a maximum or a minimum. You don't even have a point necessarily on here where your derivative is equal to 0. That's not necessarily even going to be the case. So here's what the end result is going to say of the mean value theorem. Let's take a look at the 2 points on the end. Okay, take a look at the end points here, and what I'd like you to do is to think about the line that connects those 2 points. So it looks something like that right there. Okay. Now our function f could have been a little bit more crazy. It could have done something weird. Okay. This one's doesn't seem too bad. But here's what the result is going to say of the mean value theorem. It says that at some point in there has to be a point c that when you take the derivative of c, you actually get exactly the same value as whatever the slope of this line is. So for example, it looks like there is a point right about, I'll call it right about there in green, where if you look at the slope of the tangent line, if you look at the derivative there of that at that point in green, it looks like the slope of that has about the same slope as the blue line right there. And so here's kind of a way to say this is there is a number c such that f prime of c is equal to basically the slope of the blue line which connects a and b, and that looks like y2 minus y1 over x2 minus x1, or another way to say that is f of b minus f of a all over b minus a. Okay, so you should think about this part right here as being like your slope, m, using your two endpoints there. Okay, by the way, another way to write this formula, if you think about multiplying both sides by b minus a, here's what you get. B minus a times f prime of c is equal to f of b minus f of a. This should actually look familiar. This should look like a lot like the point slope form of a line, where this is like y minus y1 equals m times x minus x1. Should look really kind of familiar there. And so for us, the value of c that we're looking for might be like right there. It actually kind of looks like there might be another point on here, c, in fact maybe two other points, where the derivative at c has exactly the same value as the slope of the line. It looks like there's probably another one right up here where if you take the derivative and you look at the tangent line there, it's probably parallel to that blue line. Maybe another point right here, somewhere like there, where you have the derivative there, also giving you a value that's the same as the blue line slope. So there could be a value c there and there. It looks like there could be more than one. But again, when it says there is a number c, again, you could substitute the wording saying there is at least one number c, such that that happens. Okay, so this is a really important result for us. We're going to take a look at a couple of kind of results that follow up from this and follow really directly from this. And the first one's going to feel pretty obvious. The second one is going to be really important for us as well. So the first one says, if f prime of x is equal to 0 for all x in the interval, think about kind of what that means for a second. That means that from a to b, you just have 0 as your output. You just have that line right there. Okay, then, I'm sorry, for f prime actually, that if f prime is equal to 0, then you're going to have a horizontal line somewhere. We don't necessarily know where that horizontal line is, but from a to b, the slope of that line has got to be 0. That means the derivative is 0. Again, that's kind of that trivial case that we had at the beginning, where we said, well, it's not all that interesting, so I'm not going to worry too much about that. But that's a pretty easy result that follows pretty directly. Here's another result that's actually going to be more important for us, especially down the road when we talk about, at the end of chapter 4, we're going to start talking about antiderivatives and kind of thinking about working backwards with derivatives. We haven't gotten there yet, but this is going to be a pretty important result for us that says what happens if you have two functions whose derivatives are equal. Okay, I want you to think about that for a second. If you have f prime of x that's exactly the same as g prime of x, the question is, do f and g necessarily have to be exactly the same function? Okay, do they have to be exactly the same? Because if it seems like that's kind of a natural thought, is to say like, hey, if you have exactly the same function, they're going to have the same derivatives. So does it work backwards? Does it go the other way? If you have the same derivative, do you have exactly the same function to start out with? And the answer is actually no. In fact, right here's a pretty easy example to think about how they might be different. Let's say f of x is x squared and g of x is x squared plus 5. Okay, definitely they both have the same derivative. The derivative of both is 2x. Okay, but they're not exactly the same function to start out with. So this should feel fairly natural though. If you have a situation where both derivatives are exactly the same, f prime is equal to g prime, then they're not, f and g are not exactly the same, but they're off by a constant. So you could put it in a couple of different ways. You could either say that f minus g is constant, or you could say that f is equal to g of x plus some constant c. Okay, so they're going to be off by some constant c. In my example down below, c is actually the plus 5 down here. That's the constant that they're off by. So this is going to be a really important result for us in the future, and that comes pretty quickly from talking about the mean value theorem. Okay, check out the next video for some examples on using Rolle's theorem and the mean value theorem. Hope you've enjoyed.